as we work through this section of functions and inverses, what we are going to discover is that the inverse of an exponential function is this thing known as a logarithm. Now, a lot of the time you'll hear your teachers and they'll just talk about a log or logs, but that's basically what they're referring to, is this fancy thing known as a logarithm. Now, when I think of logs, I like to think of it as a notation that allows us to make the exponents the subject of the equation. So actually, logs are extremely helpful. And another really cool thing about this section is that there are so many real-life applications. And that's really how it gets tested. So let's have a look at exactly how we can make the exponent the subject of the equation. That's going to help us to solve when we don't know what the exponent is. In other words, when x is the exponent. So here we have a standard exponential equation. X is equal to b, whatever b is, that's the base of our exponent, to the power of y. But let's say we needed to solve for y, which definitely happens in some of the equations we encounter. Then what we can do is we can use logs to help us make y the subject of the formula. So our exponent becomes the subject. We then write down log, and the base of the exponent then becomes the base of the log. And then the x, which was on its own, is then part of the log. So y is equal to log x with a base of b. Let's practice getting things from exponential to logarithmic notation and logarithmic notation back to exponential. So here we have an example. Express the following in logarithmic form. So at the moment it's exponential form. What they are actually saying is we need to make y the subject of this formula. So just to recap, when we wanted y to be the subject of the formula, we put it on its own. We kept the base as the base of the log, and then what it was equal to, the x, became part of the log. So let's do the same thing. You'll see it's actually very straightforward. So we want to take our y and make that the subject of the formula. So y is equal to, now the base here was 3, so when we write our log, we're going to write it with a base of 3 and then x. So y is equal to log x with a base of 3. Okay, and then the next one, express the following in exponential form. So now what I've got is logarithmic form, and I need to go back to exponential form. Okay, so what does that mean? That means the thing that's on its own was originally my exponent, and the base stays the base. So that's always how I like to remember it. So I'm going to say, okay, well, 5 to the x, and then whatever is left, that was what was originally on its own on the other side, is equal to y. So 5 to the x equals y, or probably more realistic to say y is equal to 5 to the x would have been the original exponential form. Okay, here's an example that is going to show us exactly why we love working with logs, because they are so practical. So we've got a financial question. Everybody has to deal with money in life, so this is very relevant. Ayanda invests, good job Ayanda, 7,500 Rand into an account that pays 5.5% interest per annum. This is compounded monthly. Okay, so we're going back to our compound interest here. We're going to have to refresh our memory there. How long will it take, rounded to the nearest year, for the investment to grow to a value of 12,000 Rand? Okay, so we need to just work out what's happening here with Ayanda's investment. And what I always like to do is I like to start by writing down the formula. So A equals P, 1 plus I to the power of N. Okay, so that's the formula. This should be given to you at grade 12 level on the formula sheet. You've just got to know which one to use. So the compound interest is raised to the power of N there. Okay, then what I like to do is I like to just write down what I know and what I need to work out. Okay, so because I've seen my formula, I can see what all the unknowns are, and that really just guides me along. I can fill those in. Okay, so A is the future value. In other words, we want the investment to grow to 12,000 Rand there. Okay, P, that's the present value. What does Ayanda start with as an investment? and that's 7,500 Rand. Then I is the interest rate. Now we've got to be careful here. Interest rates per annum compounded monthly. So in other words, we're going to take our interest rate, which is 5,5%, okay? Because it's a percent, we're going to divide by 100. But because it's compounded monthly, we're also going to divide by 12. So I like to just go 1,200 there. So that's basically my number of compoundings. So 12 times 100 because of the percentage. Okay, you can write that however you like. I like to do it all in one step like that. It makes my calculation just a little bit simpler. Okay, and then the other thing that changes is the n value. So we want to know how long, that was actually the question, how long will it take? Okay, n is my unknown, but I've got to be a bit careful here because it is compounded monthly. I need to adapt. Okay, so let's say that it's going to be x time periods multiplied by the 12. Okay, so 12x because it's compounded monthly. All right, now that we've got that, we can substitute into our formula. So we've got 12,000 equal to 7,500. 1 plus the I we've written there as 5,5 over 1,200 to the power of 12x, where x is the amount of years that we want to work out. Okay, so now I am going to, believe it or not, be able to use logs to help me with this, but I'm going to neaten it up first. Okay, because my unknown is in the exponent, that's why I want logs to help me out, because logs help me make an exponential unknown into the subject of the formula. Okay, so the first thing I suggest we do is let's divide both sides by 7,500 Rand, because then I'm going to have that exponent just with the bracket that it's relevant to. So here I wouldn't do too much simplifying because I'm going to lose the accuracy, but we can at least cancel some of those zeros. So I'm going to leave this as 120 over 75 for now, okay, is equal to, and then on my calculator I'm going to just work this out, and I'm going to leave it as a fraction 2. Okay, the reason why I'm doing that is because often students lose marks because they round off too soon. So either we can get a decimal, but we need to write down all the decimal places, or we can keep this as a common fraction and only round off the final answer. And so that's what I find easiest to do. As long as you get to the same final answer, you are welcome to use whatever method you are most comfortable with. Okay, so now what we've got is we've got a base here of this fraction, 2,411 over 2,400. That's the base. Okay, and then let's say this is our unknown here. We want to make this the subject of the formula. Needs to be subject. Okay, and then we've got our other, the answer almost, that's going to become part of the log. Okay, so we're going to write this now in log form. Remember, the base remains the base, so 12 to the x becomes my subject. And now I'm going to say log with this base here, 2,411 over 2,400. Let's write that neatly, 2,400. And then that is the log of 120 over 75. Okay, and now what I can do, all in one step, especially when it comes to finances, like I said, we actually don't want to round off anything until we're at the final answer. So let's get all of this into one fraction. So now I will literally be solving for x. And on my calculator, I've got the log button just underneath the on button. So I'm going to press that. In the base, I'm going to type 2,411 over 2,400, and then there in the subject bracket I'm going to put 120 over 75. Okay, and then once I've worked that out, I'm going to divide it all by 12, and that gives me an answer there of 8,565, etc. Okay, but have a look at what they've specifically said here. They said, how long will it take? Rounded to the nearest year. Okay, and so therefore we need to then say x is equal to 9 years. Okay, after 9 years, Ayanda's investment will have grown to 12,000 Rand. Okay, so that is basically the application of logs. What we've done is we've done an age-old thing. We actually were introduced to compound interest already in grade 9, but now we've added the fact that we can find out how many years something was invested for simply by using this logarithmic notation. Now, most of the time when logs are coming to us, they are coming in the form of some sort of context, so like we've just seen with the finance question, or they are coming when we're working with exponential functions and we want the inverse. Okay, but we are required to be familiar with these things known as the log laws, which are kind of like the laws of exponents, but now applying to the log version. Okay, and they're actually very simple, and I really enjoy solving problems by using the log laws because they always work out quite neatly in the end. Okay, so if we've got a log of a base, or log AB to the base B, basically because this is being multiplied, we add the logs. Look how similar that is to exponents. Remember when we were multiplying the bases, we added the exponents. So it's a very similar approach. Okay, if we're dividing A and B, then we are subtracting the logs from each other. Okay, this one here is so helpful. If we've got log base B of A to the power of n, what we are allowed to do is move that n down to the front of our log. Okay, I love this one. And then finally, log base B of A, what we can do is we can take the log of the number, log A, and divide it by the log of the base, log B. Okay, so those are the log laws, and then we also have two little deductions that we can make, and they look like this. So log base B of B is equal to 1, okay? And if you think about that logically, if you were to rewrite it in exponential form, it would make perfect sense. B definitely does equal B to the power of 1. Okay, and then similarly here, log base B of 1 is equal to 0. Okay, again, we'll take our base. B to the power of 0, anything to the power of 0 does equal 1. So that's why we have those two deductions that we can make. Let's look at these log laws in action because, like I said to you, they actually work out quite nicely and they're quite fun to work with. So here we've got log base 9 of 3 plus log base 9 of 27. So the first thing I do is I check, are the bases the same? And they are. And that means I'm allowed to apply a log law here. And the law says when we're adding the logs, it means we actually can multiply those two numbers. So we can then rewrite this as log, it stays base 9. And then in the brackets, 3 times 27. Okay, so that's log 9 on our calculator. 3 times 27 is 81. Okay, now what I notice, which is fantastic, is that 81 is actually just equal to 9 squared. So I'm going to rewrite that then as log base 9, 9 squared. And then we can apply that other law where we're allowed to move the exponents down to the front of the log. So this is then going to become 2 log base 9 of 9. And what did we deduce earlier? We saw that if the base and the number are the same, that is essentially equal to 1. So this is actually just 2 times 1, which is equal to 2. So there we've taken something that looked quite complex, and we have simplified it right down to a 2. Okay, question 2 here says log base 8 of 16 plus log 5, 25. Okay, so the first thing I'm noticing is that these two bases are not the same. So whenever the bases are not the same, I jump straight over to the rule that says we can take the log of the number, log 16, divided by the log of the base. Okay, so I'm going to do that in both instances. Log of the number divided by log of the base. Okay, and then what we need to do is we need to get prime basis. For anything that's not a prime, that's always a go-to. It's very similar to how we would have approached an exponent question. Okay, so 16 is actually 2 to the power of 4. 8 is 2 to the power of 3. And 5 squared is equal to 25. Okay, this is already looking so positive because look at this, log 2, log 2, log 5, log 5. So I'm definitely making progress. Okay, let's apply the log law that says we may move the exponent down to the front of the log. And we're going to do that for all of these. Okay, so we then got 4 times log 2. It's actually not necessary to do the bracket there. 3 times log 2 plus 2 log 5 over log 5. Okay, and now seeing as though there aren't any plus or minuses inside the numerator or denominator, I am allowed to cancel. So log 2 is going to cancel with log 2 here, and log 5 is going to cancel with log 5 here. So that leaves me with 4 over 3 plus 2 over 1. And then however you work that out, the question probably would have said no calculators allowed, because the calculator obviously can do all of these logs, but they actually want to check that we know the law here. So this is going to be 1 1/3 here plus 2, and so that's going to give us a final answer there of 3 1/3. Okay, you could also then get a common denominator and add those together, but sometimes when you're working with a whole number, it's quite easy just to add. Let's look at one final example now. This might look very scary, but actually, let's see how we can apply those log laws. So don't panic yet. Log base x minus 1 of x squared minus 1 minus log base x minus 1, x plus 1. Okay, the bases are the same. That's always the first thing I check when I'm dealing with these things here, is are the bases the same? And since they are, I can then apply the log laws straight away. And the law says if I'm subtracting the logs, it means I was dividing the numbers, or I can divide the numbers, depending which direction you're working in. So log x minus 1 is the base there, and then what that contracts to is x squared minus 1 over x plus 1. Okay, now what we can do is we can factorize this. This looks like the difference of squares. So let's do that. So we've got log to the x minus 1 base, and then here we're going to have x plus 1, x minus 1 over x plus 1. Okay, what do we notice here is that we've got things that can cancel. X plus 1 can cancel with x plus 1. So now we've got log base x minus 1 of x minus 1. And now let's apply, oh, we don't even need to apply that log law. I was going to say log of the number over log of the base. But what do we know? When the base and the number are the same, that is simply equal to 1. That's one of our log deductions.